Go be downhill problem number 1, velocity, or problem number 2, velocity. If we continue to disregard friction, will slope be a contributing factor to our rider's velocity? Well, let's go ahead and see. Let's start by assuming that the trail our rider takes from top to bottom is the hypotenuse of a right triangle. And I'm going to go ahead and try to write that in for us here. I'm not going to use a ruler, so excuse my lack of straight lines, but I'll do my best. So let's go ahead and draw in our right triangle here. And let's make this connection. Again, we're going to disregard friction. We know that the vertical displacement was 610 meters. We know that the hypotenuse here, the actual trail the rider is going to take, is 1220 meters. We treat this as a right triangle. We need to find this angle here to determine constant slope. So our ultimate problem again is going to come back to, can we find velocity here in meters per second, and does this slope have anything to do with this velocity? Well, let's go ahead and solve this with a 3-part plan of attack. The first thing we want to find here obviously is our angle, and from that angle we found our constant slope. If we know we have a constant slope, we can find our constant acceleration in the second part of our attack, and then we can use that acceleration to find our velocity. So let's go ahead and solve this problem like so. Let me again draw this in for us. We know that this leg of the triangle sure I'm on the right screen here. This leg of the triangle is 610 meters, and this leg of the triangle, the hypotenuse, is 1220 meters. Our first objective is to solve for that angle there, or theta. So let's go ahead and plug in a little trigonometry. We know that the sine of that angle should be equal to opposite over hypotenuse. So that's a 610. I'm going to leave the meters off because they're going to cancel. Divided by 1,220. And to get theta by itself, we're going to divide through by sine. So we know theta is going to be equal to inverse sine of 610 divided by 1220, which is just a half. And if you plug inverse sine of 0.5 into your calculator, you'll find that the angle that we were trying to determine is 30 degrees. So in this part of the problem, we've just found our angle for our constant slope to be 30 degrees. Second part of the problem, using that information, that 30-degree angle, we're going to find our constant acceleration. So plugging that into this equation, acceleration is equal to acceleration due to gravity times the sine of theta. That's going to mean gravity due to acceleration, or acceleration due to gravity, excuse me, 9.8 meters per second squared is going to multiply by the sine of 30 degrees, which we know to be 0.500. 9.8 times 0.500 gives us our answer for our constant acceleration, and that is 4.9 meters per second squared. So we've already found our angle and our constant acceleration. We now can go ahead and solve for velocity. If we go ahead and solve for velocity, we know that here, velocity squared is equal to 2 times acceleration times distance traveled. Therefore, to get rid of that exponent. We know that velocity is going to be equal to the square root of 2 times acceleration times distance traveled. So again, plugging that in, we know that our acceleration, I'm going to leave the units out, was 4.9 meters per second. We know that the distance that our biker took to get down the trail was 1,220 meters. When I plug this into my calculator and take the square root, I get a velocity equaling 109 meters per second, which you'll note is the same exact answer that you got in problem number 1. So we know that that equates to 240 miles per hour. Now again, if you think that that's an unreasonable speed of our rider moving down the side of the mountain there, you are correct. Also considering the fact that the land downhill record is 105 miles per hour by Frenchman Eric Perron as he was bombing down the side of a Nicaraguan volcano. So 240 miles per hour is very, 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 very fast. So it is fair for us to assume that friction due to a bike contact on the trail, friction due to brakes on the bike wheels, friction due to air resistance plays a huge role in how fast our rider bombs down the side of this mountain. But the video did give us a clue as to what this speed was. And if you recall, and this is pretty easy to calculate, if we know that his trip was 1,220 meters, if you watch the YouTube video, you found that he accomplished that in 74 seconds. Assuming that that was real time, can you calculate his real velocity, considering all of the friction involved, in meters per second, first of all? So if you'd find that in meters per second, and then if you'd go ahead and convert that to miles per hour, you'll be able to actually see what his real velocity was. And again, this is a vector quantity, so we'll use the word velocity instead of speed. And if you do the math here, you end up with an answer here of about 16.5 meters per second, which translates to miles per hour of about 36.3 miles per hour. Now that's pretty fast going down that 2,000 foot vertical, but it's nowhere near 240 miles per hour. So we know that the resistance due to friction here is huge in determining the ultimate velocity of our rider bombing down this 2,000 foot vertical in the Gobi Desert.